Dear students, welcome to the cryptography and network security subject. We are in module 2. In this particular session, we are going to learn about the security of RSA. In the previous session, we have seen what actually RSA algorithm is with a simple example. Right? In this particular session, let us see the security part of the RSA. As I have mentioned in my previous session, when it comes to RSA algorithm, the security part of it is the most studied aspect of the modern cryptography. Basically, the security of RSA relies on the mathematical difficulty of factoring the large integers. So when I say this, in the algorithm earlier we have seen n, right? The variable n. So this n, it was used for modular operations. Am I right? Now, actually, how we got this n? This is nothing but the product of two prime numbers. So, when I say prime numbers, basically we are going to get the large prime numbers, right? It is a very large prime number, in fact. So, when I'm having these two large prime numbers, now what is the difficulty here is how quickly or how much time does it take to factor this n is what the security of RSA depends on, right? So here for RSA, we generally make use of large key sizes so that we will be able to implement more security in it. Though we have implemented highest security, this RSA algorithm is vulnerable to several attacks. So, to mention a few, it is vulnerable to your brute force attack, mathematical attack, timing attack, hardware fault based attack, and chosen ciphertext attack. Now, let's see what each of these says. The brute force attack, generally in security terms, we see it as BFA, right? So, what is this brute force attack? In case of your brute force attack, an attacker would be using all possible ways of attacking a particular system or breaking that particular crypto system, right? So in this case he will be trying to use all the possible private keys. As you know, this private key is kept secret, right? So nobody will be knowing it. Now what he does is he wants to listen to the message at any cost. So he will be trying with all different possible keys. So what we have to make if I want to provide a defense against it, against that particular attack. If I want to prepare a defense, then what should I do? So what we should do is we have to use large key sizes. So nowadays we find this 2048 bit key size for RSA even more we can make use of. So more larger the key size is, it is more secured. However, there is again disadvantage associated with that. If the key size is larger, storage requirements also come into picture. Time taken for encryption and decryption also comes into picture. So general, as we say generally, right? So if you want to achieve something, you might have to compromise something else. Right here, if you are trying to achieve security, you might have to compromise the performance part of the RSC, right? Next, coming to the mathematical attack, as I told about, as just how I mentioned about this factor n, right? So you have this n, which is product of two prime numbers. Now, when I know what is n, the thing is, how will I derive this p and q? Is it easy to derive me this p and q? Is it easy for me to derive this p and q, or it takes quite a good amount of time, right? So once if I am able to do this, then the next thing is about recovering D, which is nothing but our private key, right? So as you know, the public key in RSA is nothing but the combination of E and N, whereas the private key is the combination of D and N. Once I know what is N, my aim would be in deriving D only, right? Because E, it will be available as the name says, it is public, so it's available in the repository. But D is what I'm not having, right? So I have to recover it. So how I can provide defense in this case against these attacks? Again, so in we here we have to use, first thing is use random prime numbers and choose it as large as possible. In the previous session, the example that we had taken, if you remember, so then I think we have taken 11 and 3 as the prime numbers. Do you think this is last prime number? No, obviously not, right? So it's very smaller prime numbers. So we have to take quite large prime numbers in order to provide the defense against this attack. Coming to your timing attack. So here what happens is the attacker is looking into the algorithm working principle of RSA. Is looking how encryption is happening, how decryption is happening, how much amount of time is required at the encryption end, what is the time required at the decryption end. So based on the amount of time required to perform this encryption and decryption, he is studying. And once he gets that particular thing, right? So if I want to get, or if I want to retrieve the private key, right, how much processing time is required, if I'm able to measure it, then it I can say that the timing attack has happened, right? So what should I do? So for this, as a defense part, what we can do is either you add delays into it, or you use an algorithm such that whatever the key size it is, it would take the same time, that is constant time is taken independent of the size of the key that has been used. So for some key sizes it is taking lesser time, for some key sizes it is taking more time. So based on that, at least the attacker would be able to guess what would be the size of the key, right? So later he can apply some other techniques to retrieve the key. So this is what we call it as timing attack. Now every time, even if it's a smaller key size, I add some delay into it and make it quite larger or quite longer, or say use an algorithm which uses constant time, be whatever the key size is, right? So that is how we can provide protection against the timing attack. Now hardware fault based attack. So here what we are trying to do is, while the RSA operation is going on, the attacker would try to deliberately cause fault in the processor, and whatever the output that we get, the faulty output whatever we get, so from that he is going to retrieve some information about the key. So purposefully the attacker himself is introducing fault in the processor during the RSA operation, such that whatever the fault output that we get, we are trying to retrieve some information out of it. So how can I provide defense in this case? In such cases, I can make use of either a fault detection algorithm, or you can have error checking in place, or you see to that your hardware is very secure, nobody will be able to tamper it. That is what we can do. And coming to the last one, it is the chosen ciphertext attack. So here, which we have already seen in module 1, right? So what he does is, he he means attacker, he is using his own ciphertext. He has generated some ciphertext from the plain text. Now what he is trying to do is, he is going to give that ciphertext into the system, and whenever that ciphertext is fed into the system, what does the decryption algorithm do? It is going to decrypt it. Now he's going to observe the decrypted output, and then he's trying to obtain a relationship between that ciphertext and the output that he has obtained. So by learning, or by with the careful observation of the relationship between the two, he's trying to retrieve the key out of it. So now what we can do for this is we can make use of padding scheme, and one such padding scheme is your optimal asymmetric encryption padding, which provides, which prevents exploitation against these kind of attacks. So to sum up the security aspect of RSA, you can say that when I say larger key size, obviously stronger is the security, but as I told, performance is at stake. Right? Since the key size is large, the performance is at stake. So generally, this is the reason why RSA algorithm, we make use of it in the key exchange and in digital signature. But for encryption and decryption, we are making use of the faster symmetric algorithms like AES. So this is about the security aspects of RSA. Thank you, students.